Friends, in the last lecture, we have discussed on the differentiability and we have seen the necessary and sufficient condition for the differentiability. Today, we will discuss on some examples. First, we recall the definition. If the function f is differentiable at point AB, if f of a plus h comma b plus k minus f of ab. Okay, this difference is called the increment of f, and this difference is equal to ah plus bk plus h into phi of hk plus k into psi of hk, where a and b are the constants and independent of h and k, and phi tends to 0, psi tends to 0 as order pair hk tends to 0, 0. Here h tends to 0, k tends to 0. In the necessary condition, function f is differentiable. Function f is differentiable, then function f is continuous and the partial derivatives with respect to x and with respect to y exist. In the necessary condition, we have seen the value of a is f of x, that is the partial derivative of f with respect to the x. Therefore, the value of a is f of x, and b is equal to f of y, that is the value of b is f of y, that is the partial derivative of the function f with respect to y. If this condition is held, then we say that the function f is differentiable. In the necessary condition for the differentiability, we have seen the function f is differentiable at point AB. Then the function f is continuous and function f of x, the function f of x and the function f of y at point AB exist. At point AB exist. In the necessary condition of the differentiability, if the function f is differentiable, then the function f is continuous at point AB, and the second condition is that the partial derivative of the function f with respect to the x at point AB and partial derivative of the function f with respect to y at point AB exist. But the converse is not true. See, in this problem, this is a given function. The function fxy is equal to x cube minus y cube divided by x square plus y square when xy is not equal to 0, 0, and value of the function is 0 when xy is equal to 0, 0. The converse is not true. That is, the function is exist, which is continuous and possess the partial derivatives. But the function f is not differentiable. At that point. Okay, now let us see the solution of this problem. First, we have to show that here. First, we show that the function f is continuous. Now let, for epsilon greater than 0, consider in mod function fxy minus at a point 0, 0, at a point 0, 0, that is f of 0, 0. Then this one is equal to the value of the function fxy is x cube minus y cube. X cube minus y cube is divided by x square plus y square minus 0. Then this one is equal to in mod x cube minus y cube is divided by x square plus y square. Then this one is less than or equal to. This one is mod of x cube plus in mod y cube is divided by x square plus y square in mod x square plus y square. But the mod of x is always less than or equal to square root x square plus y square, and mod of y is always less than or equal to square root x square plus y square. Therefore, here we write this one is less than or equal to, that is here the mod of x is less than or equal to square root x square plus y square, and mod of y is less than or equal to square root x square plus y square. Therefore, here we write 2 times in bracket x square plus y square bracket raised to 3 by 2. Okay, 2 times x square plus y square bracket raised to 3 by 2 is divided by x square plus y square. Since the mod of x is always less than or equal to square root x square plus y square, and mod of y is always less than or equal to square root x square plus y square. Here, this one is less than or equal to mod of x cube plus mod of y cube is divided by in mod x square plus y square. But mod of x is always less than or equal to square root x square plus y square, and mod of y is always less than or equal to square root x square plus y square. Therefore, this one is less than or equal to 2 times in bracket x square plus y square bracket raised to 3 by 2 divided by x square plus y square. Then this one is less than or equal to 2 times here x square plus y square bracket raised to 3 by 2 raised to minus 1. Then here we get the square root of x square plus y square. Okay, that is this one is equal to x square plus y square bracket raised to 3 by 2 minus 1. That is equal to x square plus y square raised to half. Then this one is less than epsilon. Then this one is less than epsilon. If here x square plus y square is less than del square, by the definition, for epsilon positive, there exists del positive in mod fxy minus f of ab is less than epsilon whenever 0 less than square root x square plus y square is less than del. Therefore, by the definition, here we write x square plus y square less than del square. Okay, here we choose 2 del is equal to the epsilon. That is, here we write where del is equal to epsilon by 2. This one is less than or equal to 2 into square root x square plus y square. But by the definition, the square root x square plus y square is less than del. Therefore, the 2 del, we choose the 2 del is equal to the epsilon. Therefore, here we write this one is less than epsilon if x square plus y square is less than del square, where del is equal to epsilon by 2. Therefore, for epsilon is greater than 0, there exists a positive number. There exists positive number del. There exists a positive number del such that in mod function fxy minus f of 0 0 is less than epsilon. For epsilon is greater than 0, there exists a positive number, say del, such that in mod fxy minus f of 0 0 less than epsilon, whenever x square plus y square is less than del square. This proves that the function f is continuous. Therefore, we say that the function f is continuous at a point 0 0. Here for epsilon is positive, there exists a positive del such that in mod fxy minus f00 is less than epsilon whenever x square plus y square is less than del square. And this proves that the function f is continuous at point 0, 0. Okay, here first we show that the function f is continuous. Now second, possesses the partial derivatives. That is, the partial derivative of the function f with respect to the x at a point 0, 0 and partial derivative of the function f with respect to y at point 0, 0. Now let us say the function f of x, that is the partial derivative of the function f with respect to the x at a point 0, 0. Okay, that is the definition of f of x. The partial derivative of the function f with respect to the x is equal to the limit h tends to 0 f of a plus h, here a and b are 0, therefore here we write f of a plus h, a is 0, b is equal to the 0, minus ab, that is a equal to the 0 and b is equal to the 0. Then this one is divided by h, this one is divided by h as a limit h tends to 0. But here the given function fxy is equal to x cube minus y cube divided by x square plus y square. Now we take h is equal x equal to the h and y is equal to the 0. Then this one is equal to the limit h tends to the 0. We write here h cube is divided by h square minus f of 0, 0. Then this one is equal to the 0. This one is divided by h. This one is divided by h. Then this one is equal to the limit h tends to the 0. That is here h cube divided by h square divided by h. Then this one is equal to the 1. Then this one is equal to, as a limit, s tends to the 0. This one is equal to the 1. The limit of 1 as s tends to 0, then this one is equal to the 1. Therefore here, the partial derivative of the function f with respect to the x at a point 0, 0 is equal to 1. Therefore, the function fx at a point 0, 0 is equal to 1. Now, the partial derivative of the function f with respect to y at a point 0, 0 is equal to, here the limit k tends to the 0. Here the definition of y, that is the partial derivative of the function f with respect to y, is equal to the limit k tends to 0. f of a is equal to the 0, b plus k, b is 0, then this one is k, minus f of 0, 0. Then this one is divided by k. This one is divided by k. Our given function is f of xy is equal to x cube minus y cube divided by x square plus y square. Therefore, f of 0k is equal to, as a limit, k tends to 0. That is here, minus k cube divided by k square. Then this one is divided by k. The function f of 0, 0 is equal to 0. Okay? X equal to the 0, y is equal to the 0. Then the value of the function is 0. Then this one is equal to the limit k tends to 0. Minus k is divided by k. Then this one is equal to the limit minus 1 as k tends to the 0. Then this one is equal to, therefore here we write the function f of y at point 0, 0. This one is equal to limit of minus 1 as limit k tends to 0. Then this one is equal to minus 1. Therefore here the function f of x at a point 0, 0, the value is 1, and the partial derivative of the function f with respect to y at a point 0, 0, this one is equal to minus 1. That is here possess the partial derivatives. Therefore, here the function f of x at point 0, 0 is equal to the 1, and partial derivative of the function f with respect to y at point 0, 0 is equal to minus 1. Therefore, we say that the function f possesses the partial derivatives at point 0, 0. Therefore, here we write the function f possesses partial derivatives at a point 0, 0. In first part, we have shown that the function f is continuous. In second part, the function f possesses the partial derivatives at a point 0, 0. Now we have to show that the function f is not differentiable at point 0, 0. If the function f is differentiable, at a point 0, 0, then by the definition, we write f of hk minus f of 0, 0. Here, the function f is differentiable at point 0, 0. If the function f is differentiable at point AB, then we write f of a plus h, comma, b plus k minus f of AB. This difference is equal to a into h plus b into k plus h into phi plus k into psi. Phi and psi tends to 0 as order pair of hk tends to 0, 0. Here, a is equal to the 0 and b is equal to the 0. If the function f is differentiable at point 0, 0, then by definition we write f of hk minus f of 0, 0 is equal to a into h plus b into k plus h into phi of hk plus k into psi of hk. Okay, here h plus bk plus h into phi plus k into psi of hk, where a and b are the constants. Therefore, a is equal to, that is the partial derivative of the function f with respect to x at a point 0, 0. Then f of x is equal to 1, and b is equal to the partial derivative of the function f with respect to y at a point 0, 0. Then this one is equal to the minus 1. Then this one is equal to minus 1. And phi of hk tends to 0, psi of hk is tends to 0 as order pair of hk tends to 0, 0. Now this implies that, okay, if the function f is differentiable at point 0, 0, then by the definition, here where a is equal to f of x, then this one equal to the 1, and b is equal to f of y, then this one is equal to minus 1. Phi and psi tends to 0 as order pair of hk tends to 0, 0. Then here this implies that the function f of hk, that is here we write h cube minus k cube is divided by h square plus k square minus 0. This one is equal to the value of a is equal to the 1, then this one is equal to the h, plus b, the value of b is equal to minus 1, that is this one is equal to the minus k, plus h into phi of hk plus k into psi of hk plus k into psi of hk. Now we use here the polar coordinate system. Put h is equal to r cos theta and k is equal to r sin theta. Now here we put h is equal to r into cos theta and k is equal to r into sin. Then order pair of hk tends to 0 0. Then order pair of hk tends to 0 0. Then this implies that r tends to 0. This implies that r tends to 0 for arbitrary theta. Put h is equal to r cos theta, k is equal to r sin theta. Then order pair of hk tends to 0 0. Then this implies that r tends to 0. S tends to 0, k tends to 0, then r tends to 0 for arbitrary theta. Therefore, we write put h is equal to r cos theta, that is r cube minus cos cube theta, that is r cube in bracket cos cube theta minus sin cube theta, h square plus k square, that is here r square in bracket cos square theta plus sin square theta. The value of cos square theta and sin square theta is 1. The value of cos square theta plus sin square theta is 1. Therefore, this one is divided by r square. Then this one is equal to h is equal to r into cos theta minus r into sin theta plus h is equal to r into cos theta into phi plus k is equal to r sin theta into psi. Therefore, here r cube is divided by r square, that is r. Then r into, in bracket, cos cube theta minus sin cube theta is equal to. Okay, here r is common in each term. Therefore, r into, in bracket, cos of theta minus sin theta plus phi into cos theta plus psi into sin theta. Then this implies that cos cube theta minus sin cube theta is equal to, here r is divided by r, since r is not equal to the 0. Therefore, here we write is equal to cos of theta minus sin of theta plus phi into cos of theta plus psi into sin theta. Here, since r is not equal to 0. Here, since r is not equal to 0. Now, taking the limit r tends to 0, then we get taking the limit r tends to 0, then we get, as r tends to the 0, then phi and psi is tends to 0. Then here we get cos cube theta minus sin cube theta is equal to, this one is equal to cos theta minus sin theta. Okay, as a limit r tends to 0, then we get cos cube theta minus sin cube theta is equal to cos theta minus sin theta. Then this implies that cos cube theta minus cos theta minus sin cube theta plus sin theta, then this one is equal to the 0. Then by simplifying we get cos theta minus sin theta into cos theta into sin theta is equal to 0. By simplifying we get cos theta minus sin theta into cos theta sin theta is equal to 0, and which is not possible for arbitrary theta. which is not possible for arbitrary theta. Therefore, we say that the function f is not differentiable at a point 0, 0. Therefore, we write which is not possible for for arbitrary theta. Okay, which is not possible for arbitrary theta, and therefore we say that the function is not differentiable. Therefore, we say that the function f is not differentiable at a point 0, 0. Okay, therefore the function f is not differentiable at a point 0, 0. Okay, this is the solution of this problem.